Hi everybody. In this video we're going to be talking about latent heat, and we've already mentioned it in our notes, but I just want to kind of show you how latent heat works, and well, first I'll describe what it means. And we're going to be using this graph right here to kind of plot how heat is transferred between phases, especially phases of water. And that's really, when we talk about atmospheric processes, what we care most about, the phase changes of water, because there's all kinds of water in the atmosphere. So latent heat, and I'm just going to write this at the top right here. Latent heat. Latent means hidden. It's you might say it's the opposite of what we call sensible heat. That was another one of your terms in the notes. Sensible heat is heat that can be, well, sensed. It can be measured by a thermometer. It's heat that causes something's temperature to change. What latent heat is the heat of phase change. Okay, heat of phase change, and so there's a certain amount of energy that goes into causing a compound, like say water, to change phase, but it doesn't actually change the temperature. So we're going to plot this right here, and hopefully that will make sense. One thing I'd like to remind you of, and I think we mentioned this in the notes, is the idea of a calorie. All right, so this is along the x-axis right here is calories, and so 1 calorie. Now you probably know that a calorie as being something that having to do with food, and they're related, but the technical definition of a calorie, okay, equals the amount of heat required to raise 1 gram of water. Oops, I shouldn't divide that. By 1 degree Celsius. Okay, let me repeat that. So you've got 1 gram of water. By the way, a gram of water is about the size of a pea, maybe, or of a blueberry. Okay, not very much water, but it's the amount of 1 calorie is the amount of energy to raise 1 gram of water by 1 degree Celsius. All right, so it's a certain amount of energy, and it is defined by how water raises its temperature when it gains heat. So let's say, for example, maybe this will make more sense if we just kind of draw it out. Let's say we have right down here, by the way, ignore this blue stray mark right there. That's just something I forgot to erase. Let's start right there at the very bottom, okay? We have a gram of water, all right, and that's what the title says, heat transfer in 1 gram of water. We've got 1 gram of water at negative 50 degrees Celsius. All right, so what phase is that? Well, it's going to be solid, right? It's going to be basically ice because it's well below the freezing point. Here's the freezing point right here. It's a negative 50 degrees Celsius. So if we take that 1 gram of water and if we add 1 calorie of heat to it, what's it going to be? Well, it's going to be 1 gram of water at... So we add 1 calorie, so we raise the... So we kind of come over here to the left a little bit, all right? We raise the amount of calories that is going into it. And so what that does is that raises the temperature to 49, all right? So you might say it's like, now it's right there where that little teeny tiny dot is. Okay, we add another calorie of heat to it, okay? Well, that raises the temperature to 48, all right? And then 47 and 46. You see what's happening right here. As we add calories of heat, the temperature goes up. Negative 50, 49, 48, 47, 46. And so if we add 50 calories of heat to it, it's going to raise it by 50 degrees. Does that make sense? All right, so here's what's going to happen. As we continue to add calories, we're going to have that happening. All right, we're adding calories of heat and we're raising the temperature. All the way up to, so if we add 50 calories of heat, we raise it 50 degrees. By the way, that's why I started at negative 50, so it would be convenient like that. We add 50 calories of heat, we raise it 50 degrees up to 0, which you probably know is the freezing and melting point of water, okay? 0 degrees Celsius. So right here we have 0 degree Celsius ice, okay? In fact, where am I going to write this? I'm going to write this down below right here. Okay, 0 degrees Celsius ice or solid. Okay, so you might think, all right, well, let's just add one more calorie and it will become what, 1 degree water, right? That makes sense, but we are leaving out the concept of latent heat. What latent heat is the heat required to put in just to change the phase. So what we're going to do is we're going to have to add 80 calories of heat just to change it to 0 degree water. So it's not going to change the temperature, it is going to just simply change the phase. And so here's what I'm going to do. I'm going to add 80 calories, so I'm starting at 50 right here, so that's another 50, and and then another 30 would be 80, right? So I'm going to go over here, that's 50, and then right to about there, I think would be about 80 calories. 50 plus, 80 is about 130, and that's where I am right there, okay? So nothing's happening to the temperature, you see right here, but I keep adding heat. So here I'm adding heat, temperature's changing, great. But now it's ready to change phase, but I need to add latent heat to change the temperature. And not until I add those 80 calories does it become from 0 degree ice. Now all of a sudden I'm going to change the color to 0 degree liquid. 0 degree water. Okay, because I had to put in that latent heat right there to get it to change. Now, if I start adding calories of heat, now the temperature of the water will go up. All right, so I add a calorie, it raises the temperature. Add a calorie, it raises the temperature. And so I'm at, let's see, what's the next main temperature for water to change phase? Well, it's going to be 100, right? So if I add 100 calories from here, so I'm starting at, what is that, like 130, okay? So if I go all the way up to 230 calories, it should raise the temperature of water by 100 degrees. All right, so I'm going to put a mark right here at about 230. Let's see, right here about. Okay. And so this is what's happening with the water now. Now that it has finally changed phase from 0 degree ice to 0 degree water, now I can start adding calories of heat and it will actually change the temperature. We call that sensible heat because a thermometer will sense that change in temperature right there. So it goes up and it goes up and it goes up and up and up and it becomes 100 degree water. Great. All right. 100 degree liquid water. Right here. All right. But once again, you might think, all right, let's add another calorie and it'll become 101 degree steam. Not quite, because once again, latent heat needs to be added. This is a different amount. Before it was 80 calories, and these may seem like arbitrary numbers. 80 calories is what is required to change from liquid to solid and back. But going from liquid to gas is even more. So I'm just going to tell you that it requires 600 calories just to change it from liquid, 100 degree liquid, to 100 degree gas. So I'm going to draw a line straight across. I'm starting at 230 right here, so I'm going to add 600, so I'm going to wind up at 830, right? So this is all just heat added from there to there, simply to change the phase. Change the phase. This is 600 calories. 600 calories of latent heat to change it from 100 degree water to 100 degree. All of a sudden, what? All of a sudden, over here, it's going to be 100 degree steam or gas. All right, which is why, by the way, you can get burned much more easily with hot steam than you can with hot water because it has all this extra energy in right here. Now, once you put in the right amount of calories to change it from 100 degree liquid water to 100 degree steam, 100 degree gas, then you keep adding more calories, and then it will keep going up, and the temperature will keep rising of that gas right there. But you would think that if we say a calorie is, the amount of energy to change 1 gram of water vapor by 1 degree Celsius, you'd think it would be a steady line straight up. But it's not true. This stair-step pattern is because of the fact that once it gets to the heating, or once it gets to the freezing melting point, or the boiling condensing point, there's a certain amount of energy that we call latent heat here and here that is required just to make that phase transaction, you might say. And that's going to make all the difference for atmospheric processes, because when, say, water in gas form condenses into water in liquid form right here, there's a big chunk of energy that is either absorbed or released in that phase change. And so if you were to say, let's say, lick the back of your hand, all right? And it's, I know it kind of sounds nasty, but just, moisten the back of your hand with your tongue, and you have liquid water on the back of your hand. And so if you blow on that, if you cause it to evaporate and turn into a gas, your hand feels cold. Why? Because it's sucking all this energy out of your hand to turn it into the gas, which is why things feel colder when they evaporate. That's how sweat works. Similarly, if you have a water in gaseous form, and if that condenses into a liquid, now all of a sudden it's releasing all this energy right here in that phase change. And so that energy can be used to do a lot of things in the atmosphere. It can be used to cause wind to blow, to create all kinds of pressure disturbances. And so this latent heat is really a big player in the atmosphere. It may seem like a kind of a trivial thing for now, but the latent heat of evaporation and condensation and melting and freezing does big things to cause the storms and the various weather events that we see in the atmosphere. So that's a little bit about latent heat. Sorry if it was a little bit long-winded, but I do want you to kind of understand that. And I will ask you if you have any questions on that to make sure you see me, and so we can clear that up. So for the meantime, thank you for watching, and I'll see you on the next one.